Assalamu alaikum everyone. Inshallah, today we'll continue talking about the block cipher. We have talked about the DES encryption algorithm, and we talk about also AES encryption algorithm, and we demonstrate how each one work in the encryption and the key generation or the key expansion. Today we'll continue the talk about the block ciphers, and we'll talk some of the, we call it, mode operation that we can apply on any algorithm. So what we're going to learn today is compare different mode of operation, and we can apply different mode of operation of DES or AES. So this mode operation we will talk about can be applied in DES or can be applied on AES, inshallah. So let's start talking about that. Now, mode of operation. Of course, you never heard about mode of operation, but in general, okay, when we talk about block ciphers, okay, we're talking about what? We're talking about form basic building block, like in order to protect the data and make the data secure. And so we have a block size, and this block size is already fixed. So, for example, in the DES, we have a block size 64 bits, and the key size is what? 56 bits. But in the AES, and the difference between them, you can see that the block size is 128 bit, is fixed, but the key is was what? We have key is 128, and we have 192, and we have 256. So if you have 10 rounds or 12 round or 14 round, this is the difference now between DES and AES, but they still have what? A fixed size block. They still have what? A fixed size of a block. Now if you want to encrypt any text, okay, or decrypt any text, okay, it's actually gonna be what? It's gonna be more than 64 bits, okay. So if you want to encrypt any text, okay, the text will be more than 64 bits. So you have to split it into what? Into more than 64 bits. So this will be 64 bits first one, and then 64 bit, and then 64 bit, and so on. Okay, so that the text size, you have a file, and the file will include page. Okay, it may contain also videos, it may contain pictures, and so on. And so the size of the file will be more than 64 bits. So we have to do the encryption for each part, or for each 64 bits of the file or the text that you want to encrypt, like how many rounds. Imagine that, how complicated is the process. Okay, so you have to split it into 64 bits for the DES, or 128 bits for AES. Now, if you want to apply the block cipher, okay, in many applications, we have to include what we call it mode of operation. So we have 5 mode of operation. Okay, these 5 mode of operation can be applied either in DES or in AES. These are defined by the NIST, which is Institute of Technology and Network Institute of Technology. Now, these mode of operation are actually look a little bit similar, but each one is fixed, the other one disadvantage. So the first one has some advantage. It is fixed by what? It's fixed by the first one has some disadvantage. It's fixed by what? By the second one. And this one is fixed by the other one. This one fixed by the other one, and so on. All right. But all of them are what? Are applied. Okay. So this mode of operation is basically a technique for what? Enhancing the effect of cryptography algorithm. So they can be in any algorithm in order to increase the increase the security and also the performance of this algorithm. So these are 5 block ciphers. Okay, we're gonna study each one of them separately and see how they work and what's the difference between them, what's the advantage and disadvantage of each one. So First of all, we need to understand the initialization vector. The initialization vector is basically, the startup of the algorithm. Okay. Now, as we can see that the AES is required, what is required, like 64 bits, and we have to split it into two halves, 32 and 32, and also the AES is required a state matrix to start the encryption and so on. Okay, so most of them require what? Require binary sequence or unique binary sequence. We call it what? We call it initialization vectors. Okay, so each mode of operation is basically required what? Required an initialization vector. Okay, the initialization vector cannot be repeated. It's a unique. All right, and sometimes it's random. Sometimes it is randomly chosen. So it has to be unique. It will not be repeated. Now, the initialization vector is used to ensure what? To ensure distinct ciphertext to produce it. Even when you have the same plain text encrypted the first time, you will get a ciphertext. If you take the same plain text and encrypt it another time, it will give you different ciphertext because you use what? You use different initialization vector. So the initialization vector to make sure that the text is what? Is unique, and the ciphertext is produced ciphertext is unique and cannot be repeated because to protect it from crypto analysis somehow. This is why it is important. So when you the main idea is that when you encrypt the text, you have the text. Okay, you put the text here, the message, and you give the key. Okay, and you will get what? You get the ciphertext. Okay, but if you apply the initial vector matrix, okay, you get the ciphertext again. If you put the same message again, okay, let's different one, and give it the same key, okay, you will get C, different C. So for the same message, we give different encryption because we use the initialization vector. All right, this is defense against the crypto analysis attack. Now the first one is called electronic code book ECP. It's a very simple one. I'm gonna go to the diagram, okay, and explain it. But in general, okay, you have the plain text. It will take it as one block, okay. As one block, and then after that encrypt it with the same key over and over and over. So you're gonna split the text into what? Into blocks. Each block is going into an encryption with the same key for all the blocks. Okay. Now you have to give him the key. Okay, and there will be an encryption text at the end, or the ciphertext will be at the end. Now, if you have a long message, and the long message will be splitted into what? Into what we call it n-bit block. It depends, 64-bit block or 128-bit block, or in between them. Now, if the last block is less than 64-bit, they're gonna do what we call it what? Padding. Okay. So for example, you have the this text, okay, and you split it into 64-bit. This is 64-bit. This is 64-bit, and so on. But the last one is very small. Okay, it's less than 64 bits. So this one is done like this. This second one, third one is okay. The third one okay, and this one is okay. But the last one is very small. So what you gonna do is do a padding. Add what? Add 0 and 1s to the end to make it what? To make it 64-bit, because it's less than what? It's less than 64 bits. So that's what happened exactly. Let's have a look at the diagram. This is how is it work. Okay, this is how is it work. So you have the data. Okay, you have the data like this. Okay, you're gonna split it, for example, into blocks. Each block goes into separate encryption way. So the first block and the same key, use the same key for all blocks. So you give it to the encryption algorithm. So the encryption algorithm either what? Either DES or ES or any encryption algorithm. And this is the ciphertext. Okay. The second block will have the ciphertext. and the third block or ciphertext. If you have more encryption, then each one will generate what? Will generate a code, a ciphertext. For each block, we will have a ciphertext. Okay. At the end, we join them together, and that will be the ciphertext. The decryption is the opposite. You give him the ciphertext. This is the ciphertext. You split it into pieces like this. So you give him, this is the first ciphertext, this is ciphertext, and then the second ciphertext. And if you have more ciphertext blocks, you have to add more stages. You use the same key that you used in the encryption. It is the same key exactly, and everywhere the same key, and you will get what? You get the plain text somehow. It's a very simple and easy. You can see that these are separated, so there's no relationship between this this and this. There's separation between them. Okay, there is a separation between them. Even in the decryption, there's no relationship between the the blocks encryption. So encryption of this first block is independent of the second block, independent of the second block, but we use what? We use the same key for each block. It's a very simple and easy one. Okay, this is what we call it, what? The ECP. Is the problem right here in the plain text or the this operation mode. Okay, there's one problem. All right, now because they are separated in the ECP, we have lack of diffusion. Because what? Because you, for each block, you will get a ciphertext. Okay, and so if you use the same key here, let's go back. For each plain text, you will get a ciphertext. Okay, for each plain text, you will get a ciphertext, and use the same key. If this ciphertext is easy, okay, then I can figure out what's the text. I can figure out what's the text. If I know the text here, then I can get the key. If I get the key, okay, that means I can decrypt the other blocks. Okay, because they have the same pattern. They have the same pattern. So if I decrypt one block, then I will be able to decrypt what? To get the key and decrypt the other block, because the encryption is separate. There is no dependency between these blocks. This is the problem. So there's no diffusion. Okay, so the guy will know exactly what's the pattern. Okay, now this is the only problem. Okay, because if you have the same text and also okay, imagine that the same text repeating here, same text repeated here, it is the same text. Let's say a name, Muhammad. Muhammad is mentioned here and here and here. So the encryption block here, in here, and the encryption block here for Muhammad will be the same in the output ciphertext. So if I see these blocks are the same, I can do the crypto analysis and find out some information about the crypton text. I can try to use it to what? To infer the key or get the ciphertext. The ECP is a little bit somehow, has some limitation, that there's no diffusion because the same pattern will be used. And if I have the same pattern produced in the ciphertext, I can guess the key or the text of the other blocks. So this is one of the things that we do not recommend to use ECP. So because it is what? It is not secure, especially if you have long message. If you have a long message, for a short message it's okay, but for long message, words will be repeated, sentence will be the same, and it's easy to have the same pattern of encryption all over. So it is not secure. Okay, now this is the encryption using ECP. You can still see the mode, the picture, but if you encrypt using other modes, the picture will be hidden. So you can see that the difference, that ECP is not really secure. So this is the first mode of operation. Okay. Second mode of operation is came to fix the problem and the advantage and limitation in the CPC. So there's a new algorithm called cipher block chaining. This mode of operation is to fix what? To fix the limitation in the ECP. To fix the limitation in the ECP. So, for example, okay, they did some change. Okay, they add what you call it an XOR operation. They add what? XOR operation. It becomes that the text encryption in each stage will depend on the next one. So the encryption in this stage will depend on the previous one, and this one will depend on the previous one. So there's dependency between what? Between the encryption. Even when you use the same key, okay, still use the same key, but it does use what? It does use the XOR. Let's see the diagram so you can understand exactly what's happening. So this is how the text happen. First of all, we have initialization vector. This is the new thing. The initialization vector is something unique. If you encrypt the same text all over again using different initialization vector, you will have different key, different cipher. So this is the plain text. Okay, it will be split into blocks. Each block goes into a encryption stage. Now, before we go to the encryption, the first block will be XOR with what? This is XOR with the initialization vector. Okay, and this goes to the encryption algorithm and with the same key. So the same key everywhere. The difference now is the XOR with the initialization vector for the first one, and also, okay, in the second stage, in the second block, we don't have initialization vector. The output from the encryption will be used as initialization vector for the second block. The output will be used for the second block initialization vector. So this is the difference between this one and the other one. In the ECP, there's no, it just goes to plain text and you got the key and you produce the cipher text. Okay, the plain text goes and then the second one is separate. But in here it's different. In here it add what the new called vector matrix. This vector matrix goes and XOR with the text before it goes into the algorithm. Then it goes to the algorithm, and the output will be considered as a vector for the next one. Okay, XOR and so on. And so on like this. So there's dependency between this. This is the difference now between the CPC and ECPs. Okay. The decryption is the opposite. The initialization vector goes and XOR with the And now this is the cipher text. Will go and to the encryption and with the vector and produce the output. The same thing here, there's dependency. The ciphertext is actually XORed after the block, after the decryption. Here we have XOR before the encryption. For the decryption, it's the opposite. You do the XOR the decryption. After the decryption. Now this is called what? This is called the CPC. It has XOR, initialization vector, and there's dependency between the encrypted blocks. Okay, so this block will be used to encrypt the second block, and this one will encrypt the second block, and so on. So this is a few things about the CPC. CPC, the most commonly used mode of operation because it's simple and still secure. The main drawback that it is sequential. It is what? Sequential. Okay. What do you mean by why it is a drawback of this one as sequential? Sequential, it goes what? It goes line, one direction. If you get the first one, okay, you will be able to get the rest of it. If you solve the first problem of the algorithm, then you will be able what? To solve the rest of the algorithm, because each one is depend on the previous one. All right, this is the problem. So the first step here depend on the second step, and the second step depends on the second. If you solve the first one here, you will be able to know the whole things. This is why a problem of having a sequential algorithm. I know it's hard to solve the first one, but let's assume that someone did it, so he will be able to know the rest. If you change one bit in the plain text or the initialization vector, okay, the ciphertext will be changed. As we said, that you may have the same text, and if you encrypted the first time, you will have a ciphertext. But if you encrypted another time with changing only one bit in the initialization vector, you will have what? You will have different encryption text. Now, yes, the third one is called CFB. CFB is basically, similar to the CBC, but there's a few differences. Okay, all right. You can see there here, instead, in the previous one, in the previous algorithm, what we used to do, we used to get plain text, and we give him the initial vector, and we do the XOR, and the output will be taken to the next one and XOR. Okay, but here is different. Okay, here we go and put the initial vector as input. See the initial vector as input, and then you do the XOR after the encryption, not before the encryption. You do the XOR with that, with the plain text. All right, and you get the ciphertext, and this one will goes to the next one. And you see that the XOR is what? Is after the encryption, all right? But in here, the XOR what? XOR is before the encryption. This is the difference. You should notice that. The XOR is before the decryption, okay? But for the CFB, no. The XOR is actually after the decryption. And the same way, you take the output and consider it as input for the second one, and so on. So the dependency between what? Between the blocks and the XOR after what? After the encryption. The decryption is the opposite way, and you can see that it's still using the same key. Still use what? Same key in all the round. The only difference is that the XOR is after the encryption, and you encrypt the initialization vector first, not the plain text. The plain text is used as an XOR with the output from the encryption of the initialization vector, and you keep going that way. This is you can notice the difference between them. Now, we have another one, it's called OFB, okay, the one before the end. The OFB is similar to the CFB. Okay, they're all similar to each other. You can see the diagram here. It is similar. We have the initialization vector. Okay, we have the initialization vector. Okay, so the initialization vector is here. Okay, this is the initialization vector, is right here. Okay, and it goes into the decryption, and we have the key, and we have the XOR. Okay, the ciphertext. Okay, and then this one goes to what? To the next one. This is one. We study this one. Okay, you can see that it does do the XOR, and then take the output as input for the second one. After the XOR, the output will goes to the second block. But in this one, no. Before the XOR, it goes to what? To the second block. Before the XOR goes to the second block. So it looks different to the previous one. The only difference is that, it does take the before the XOR and give it to the next block encryption. And then after that, the XOR is gonna happen anyway. So this is the encryption here, and then before the encryption, before the XOR, I have to send it to the next block and so on. So this is the difference between what? Between OFB and what? And CFB. So both of them FB, but the different is the XOR. The XOR either before or after you give the output to the next block. Okay? But in the first one, there is no send to the next block. They are separated. The last one is called the counter. The counter is a little bit different somehow because it has a counter. It does not have only one initial vector. Each block will have a counter. This counter matrix is a random one, and for each block we will have a random one. Let's see. All right, so this is the counter. We have actually a counter 1. Now there's no initialization vector. We have counter 1 for the first block, counter 2 for the second block, counter 3 for the third block. And how many blocks we will have counter? We will go and put the counter into the encryption and use the same key. All of them will use the same key. Okay, but after the encryption, okay, there's separation. They are not what? They are not depending on each other. They're separate. All right. After the encryption, the output will be XOR with the plain text. So there is no initialization vector. Okay, and there's no output going to the next stage. Each one is separate. Okay, so this counter has similarity from the first one because we have dependent encryption block, and also we have the XOR after the encryption, similar to the CFB and EFB. All right, so here we have XOR, but it does not use initialization vector, it uses counter. So previously we used the initialization counter, and then we took this to the second one and take this to the second one. This one decided not. We should keep them separated. We should keep them separated. Instead, we should have an initial vector separately for each one. So we call this initialization vector as counter 1, counter 2, counter 3. This is why we call it counter algorithm or counter mode of operation. So these are the differences between them. This table summarizes the whole encryption mode, starting from ECP, CPC, and CFP, OFP, and CTR. You see, now this is a description for each one. It's already mentioned in the slide. And this is what a typical application for each one. So for this ECPE, ECP is not secure. Okay, it's not secure. It has some limitation, but it uses secure transmission of single value only. But for long value or long message, it cannot be used. All right. For Cipher block CPC, it fixes the problem with the ECP, and now it can be used as what? It can be used as general purpose block transmission and can be used for authentication as well. For the CFB, it uses the initial vector matrix and the XOR, so it can be used the same thing here, the same thing as the CBs. Same use application as the CPC. So the CPC and CFB has the same application. Even the OFB, okay, it has the same first one, okay, but cannot be used for authentication. No authentication cannot be used here. The last one is counter. All of them can be used for general purpose block oriented transmission, and this one counter is useful for high speed requirement. If you want a high speed thing or a good encryption, or you want to deliver anything faster than the others, should use the counter block.